In this screencast, we're going to take a look at energy in orbits and escape velocity. The first thing we're going to look at is gravitational potential energy. Now, historically, I've written it this way, but the College Board prefers U sub G, where U describes mechanical energy, and the subscript G in this case is the specific type of mechanical energy. Now, typically, gravitational potential energy requires adherence to some reference plane. So usually we'll use the formula mgh, where h asterisk is some arbitrary height above a reference plane, which the user gets to define. When we're dealing with large systems and cosmology and big systems like a solar system, we have a sun and some distant planet P. We don't have some arbitrary reference point on the surface of the planet or the sun. We use a different formula. Now, the formula is given to you on your yellow equation sheet, so you don't have to prove it. And it becomes negative g times the mass of object 1, in this case the mass of the planet, times the mass of the sun, over the separating distance. It is not squared as it is in Newton's law of gravity. Keep in mind that this negative sign presents a bit of a problem. Really what it means is as the planet were to leave away from the sun, being pushed out in this direction, as it approached infinity, way out here, we would say that the gravitational potential energy at that plane would be zero. Think of this in terms of limits. So basically, if this is infinity and the gravitational potential energy at that point is equal to zero, then we can say that as we get closer and closer to the planet, the gravitational potential energy becomes more negative. It's just a convention. A lot of students get confused with it. So we can say here that U sub G is equal to zero, and at some different plane, as we get closer and closer to the planet, we can say that U sub G would be some large and negative value. So U sub G in this case is going to be negative. Okay, that's just by standard convention. So now we have this new expression that will be given on your equation sheets, but you should be familiar with, that describes gravitational potential energy. Now there's a few things that we can do with this. We can work on a couple of derivations involving circular orbits. The first one, and we're going to get back to energy in just a second, the first one is describing a stable orbit. This one has been done in the AP Physics 1 class, but if I were to describe stable orbits, we know that we could derive a formula for a stable orbital velocity by setting the force of gravity equal to the centripetal force. If I were to draw a planet and some rotating or orbiting satellite, we would see that the only force acting on it at this point right here would be the gravitational force of attraction. That's it, F sub G. So that is the net force, or in circular motion, the centripetal force. So that becomes G times the mass of the planet times the mass of the satellite over R squared is equal to M, the mass of the satellite, times V squared over R. Now when we're solving for the stable orbital velocity, we can see that one of the r's on the left cancels out with the r on the right. The mass of the satellite goes away. This is very important, so it doesn't matter how massive the satellite is. There are many questions I've seen in the College Board question banks that deal with whether, what happens when an astronaut drops a hammer while in orbit. Well, the mass of the orbiting satellite, the hammer or the astronaut in this case, doesn't affect the stable orbital velocity. So we get G times the mass of the planet over R under the square root sign is equal to that stable orbital speed. So that would be something that you need to know solving for stable orbits. Let's keep moving. Next thing we're going to look at is escape velocity. Escape velocity, by definition, is the velocity required in order to completely escape the gravitational field of a particular body, in this case a planet or even a sun. So let's go ahead and show how that can be solved for, and then we can actually take a look at what this is for planet Earth. In the escape velocity, we would say that the total gravitational potential energy possessed by the object plus the kinetic energy that it leaves the surface with must eventually be equal to zero. The idea is that if the object starts here at the surface and goes away from the surface, that it's able to at least get to infinity away. It doesn't need to retain any kinetic energy at that point. We can say that UG gravitational potential energy plus UK is equal to 0. In other words, I could also say that UK is equal to negative UG. And then substituting for kinetic energy, I get 1/2 mv squared. And substituting my new expression over here for gravitational potential energy, that becomes negative G, but it's the negative of the negative, so they cancel out. That's positive G, mass of the planet, mass of the sun, divided by the separating distance r. By the way, the kinetic energy was the mass of the object. It's actually not a satellite if it's leaving, so that's perhaps a poor use of subscripts. Let's just call that subscript 1. And so we can see that they're going to go away anyway. The mass of the object leaving doesn't matter. I'm going to multiply both sides by 2. This becomes v squared is equal to 2g mass of the planet divided by the radius. And then I'm going to take the square root of both sides. So I get v is equal to 2 times g mass of the planet over this kind of separating distance r, or the radius of the planet in this case. And so basically this expression here is what I will use for escape velocity. In the last little piece, I'm going to derive an expression for kinetic energy, or U sub k, for an object that is in a circular orbit. And so if it's in a circular orbit, I can say that Fg, force of gravity, is equal to F sub c. This should look familiar from our work previously for stable orbital velocity. That becomes g times the mass of the planet times the mass of the satellite over r squared is equal to mass of the satellite v squared over r. I'm going to solve the expression on the right for v squared. We see again that these cancel out. I get one remainder here with that, and I get an expression for v squared. It's equal to g mass of the planet over r. And I'm going to use that for the standard kinetic energy formula, 1/2 mv squared. So now I'm going to take this expression for v squared and substitute it here. And I ultimately get 1/2 times the mass of the object, whatever is rotating or whatever is moving, the mass of the satellite, times the mass, times v squared. So v squared becomes g mass of the planet, forgot my subscript there, all of that divided by r. So if you take a closer look at that, I can basically rewrite it as g times the mass of the planet times the mass of the satellite divided by 2r. And if you look really carefully at that and compare it to our expression for gravitational potential energy, you'll see that it's A, positive, and B, looking almost identical with the exception of the 2 in the denominator. It's basically 1/2 the gravitational potential energy. So this is an expression for the gravitational potential energy. I'm sorry, not the gravitational potential energy. It is an expression for the kinetic energies. Let me get rid of that and rewrite that. It's an expression for the kinetic energy for an object that is in a circular orbit. Now, if it's in an elliptical orbit, the only difference that I ultimately have to make is replace the r with an a, where a is the short or minor axis. So now I have an expression for kinetic energy. And perhaps you can see when you look carefully then that the total energy, which is equal to the gravitational potential energy plus the kinetic energy for an object in a circular orbit, ultimately would look something like this. So I would get negative g mass of the planet, mass of the sun over r, mass of the planet, mass of the satellite, my mistake, plus the value for kinetic energy that we just established, g mass of the planet, mass of the satellite over 2r. And so really what we get in this case is just now the negative g times mass of the planet, mass of the satellite over 2r. Alternatively, I can just say that the total energy, U sub t, is just equal to negative the kinetic energy.